Okay, so this is the z-score formula, ladies and gentlemen, and whether you're computing the z-score for a data value coming from a sample or a population, notice the only difference is the symbolism changes, but the formula is essentially the same. Okay. All right, suppose the mean height of an adult man is 70 inches with a standard deviation of 4 inches. Meanwhile, the mean height of an adult woman is 65 inches with a standard deviation of 3.5 inches. Suppose a man is 66 inches tall and his wife is 63 inches tall. What is the relative position of their heights relative to other men and other women? See, it's kind of hard to compare the heights of men and women, ladies and gentlemen, because, well, you can see for the different genders here, we have different means and standard deviations for heights. And so it's like comparing apples and oranges. So what we need to do is we need to level the playing field here, and we need to convert these heights into z-scores. And by comparing the z-scores, then we'll be able to see, which height is relatively taller than the other one relative to their particular data set. Okay. So if a man has a height of 66 inches, where the mean height for adult men is 70 inches and standard deviation height is 4 inches, we get a z-score of -1 for the data value 66 inches. For the woman that is 63 inches tall, her z-score would be 63 minus 65 divided by 3.5, which is -0.57. Okay. All right. So bottom line, ladies and gentlemen, is this. Although, yes, the man is taller than a woman by 3 inches, as far as their relative tallness is concerned with their particular data set here, it appears that this man that's 66 inches tall would be shorter for the men data than the woman who is 63 inches tall for the women's data. Because -1 indicates that the man's height of 66 inches is 1 standard deviation below the mean of all men heights. And -0.57 indicates that 63, the height of a woman, is only 0.57 standard deviations below the mean of all women heights. So relatively speaking, this man is shorter for the men, for their particular category, the men data, as opposed to this woman who is actually not as short as the man, relatively speaking, for their own data sets. Does that make any sense? So relatively speaking, this man is shorter for the men data as opposed to the woman. The woman is not as short as the man when you compare the woman to the women's data. That's what these z-scores are indicating. Okay. All right, percentiles. What are percentiles? Well, percentiles are numbers that basically partition your data set up into 10 equal size intervals. Okay, excuse me. They are numbers that partition your data set up into 100 equal size intervals. Percentile, percent means per 100. Okay. All right, 1% of values are less than the first percentile, 2% of all the data values are less than the second percentile, 20% of all the data values in a data set are less than the 20th percentile value, and so forth. Okay, so like if you took an SAT exam and let's say you scored in the 99th percentile, is that a good score or a bad score if you score in the 99th percentile? Good or bad score? Good. Well, that's a very, very good score, because that means 99% of all the other scores were lower than your score, and only 1% of the scores was higher than your score. Okay, if you scored in the second percentile in an SAT exam, that means you'll probably be taking it over again, as 98% of the scores are higher than your score, and only 2% are lower than your score. So that's what a percentile value is. All right, here's an interesting graph. This graph shows the percentiles for weights for girls under the age of 18. The highlighted numbers show that an 11-year-old girl that weighs 82 pounds is at the 50th percentile. In other words, 50% of 11-year-olds weigh less than her. Well, let's see if we can try to find that value on the graph. Liz, I'm on the horizontal axis represents the age of the girl in years. The left vertical axis represents the weight of the girl in pounds. The right vertical axis represents the weight of the girl in kilograms. Okay, 1 pound is about 2.2 kilograms. So there is a little disparity between the left and the right vertical scales here. Now, if you look at an 11-year-old girl here, you got to go down to the horizontal axis to 11, and you go up, and you strike. Notice we have different curves here. These blue curves here, the lowest blue curve is the 5th percentile curve. The next higher up curve is the 10th percentile, then the 25th percentile, 50th percentile, 75th percentile, 90th percentile, and the top blue curve is the 95th percentile curve. So if you look at an 11-year-old girl and you go up and you strike the 50th percentile curve, you can see, and then project it horizontally back to the vertical axis to the left, you can see that 50% of 11-year-old girls have a weight that is less than 82 pounds. So 82 pounds, ladies and gentlemen, would be the 50th percentile of the weight of 11-year-old girls. Does that make sense there? 50% of 11-year-old girls would weigh less than 82 pounds. 50% of the 11-year-old girls would have a weight greater than 82 pounds. Make sense? Right, suppose we want to find the 90th percentile for 17-year-olds. Well, you got to go down on a horizontal axis to the age of 17. And then what you do is once you strike 17 down here, you would have to project it up to the 90th percentile blue curve. So we have to go all the way up till we strike the 90th percentile curve right here. Then we project it horizontally back to the vertical axis to the left, and we discover that 160 pounds is the 90th percentile weight of all 17-year-olds. So 90% of 17-year-old girls would weigh less than 160 pounds, and 10% of 17-year-old girls would have a weight greater than 160 pounds. Any question? Now, how would we construct a percentile graph? Well, they can be basically constructed in the same way that a cumulative ogive graph was constructed in the past. Although we would add another column called a cumulative percentage column. That's the only difference. All right, so this is an interesting diagram here. All right, I have a question. What would be, okay, listen to my question. For all 15-year-old girls, what would be the 50th percentile weight for all 15-year-old girls? Approximately, what would be the 50th percentile weight for 15-year-old girls? Anybody?
120.
Yeah, might looks very close to 120, maybe just a smidgen above, maybe 121 pounds. But that is correct. And so therefore you go on down on a horizontal axis, you go over to 15 years of age, go vertically up till you hit the 50th percentile blue curve, project it horizontally back to the left vertical axis, and you see that it appears that the 50th percentile weight for all 15-year-old girls is about 121 pounds. So 50% of all 15-year-old girls have a weight less than 121 pounds, and 50% have a weight greater than 121 pounds. Do we understand how to read this graph here? Okay. All right. How do we find percentiles? Well, ladies and gentlemen, we have to compute what's called a percentile rank value. And I'm going to let you in on a little secret here. This is one of the bizarre things about the field of statistics. There is, ladies and gentlemen, no universal way of computing percentiles in statistics. I'm going to say that again. There is no universal way of computing percentile values in statistics. Excel spreadsheet might give you a slightly different value for a 25th percentile than your TI-84 calculator will give you. versus maybe a stat software program such as Systat or SAS or Minitab. They might give you slightly different values for the 25th percentile. So, because there is no universal way to compute percentile values, as far as the way we're going to compute them in this class, is we're going to adhere to the way the textbook teaches us. And the way the textbook teaches us is going to be shown in these PowerPoint slides here. All right. So, ladies and gentlemen, when you go to do anything in Alex and they're asking you to compute a percentile value, please adhere to this method here. Okay. All right. So to compute the percentile rank of a data value X, we would use this formula here. And the percentile rank is going to be equal to the ratio of the number of data values that are below our data value X plus a half divided by the total number of data values in the data set times 100. All right, here's an example. Suppose we have this small data set, and notice it has been ordered from left to right, smallest to largest. That's also critical to find percentile values, is your data set has to be sorted or ordered. To find the percentile rank of data value 13, first we note how many observations are less than 13 in this data set. There's 1, 2, 3, 4 data values that are less than 13. That goes in for the number of values below X, part of the formula. So 4 plus a half divided by the total number of observations in the data set, which is 8, which is 4.5 divided by 8 times 100, gives us a percentile rank value of 56.25. All right, we have a decimal percentile rank value, and when that occurs, we always round to the nearest whole number. So 56.25, we would round off to what? 56 or 57? What's this closer to?
56.
56. So we're kind of down rounding it. All right. So therefore, the data value that has the data value 13, ladies and gentlemen, in our data set, okay, would be the 56th percentile of this data set. So 13 in this data set is the 56th percentile, meaning 56% of your data lies below 13. And what would that be? 44% of your data lies above it. Okay. Now, this method not only works for small data sets, but also works for larger data sets. All right. So this is the method we're going to use to compute percentile values using this formula here. Now, in order to determine the value of a specific percentile value for a given data set, we are going to use this formula. If the data set has n data values in it, and we want to find the pth percentile of a particular data value, first of all, what we're going to have to do is we're going to have to compute, okay, the rank, if you will, of that percentile value by taking the number of observations in the data set, multiplying it by the percentile value we wish to find, dividing by 100. Now, there are some strict rules here that we're going to adhere to. If the number C, after doing this computation, is not a whole number, then we always round up to the next whole number. We round up to the next whole number. The pth percentile then would be the cth number in the data set, represented as the data array sorted from least to greatest. And again, your data has to be sorted. If the number C after computation using this formula is a whole number, then the pth percentile is going to be the value halfway in between the cth number in the data set and the C plus 1th number in the data set. So again, if C is a decimal, we round up. And the pth percentile then will be the cth number in the data set. If C is a whole number, then the pth percentile will be halfway in between the cth number and the C plus 1th number in the data set. So using our example before, if we want to find the 25th percentile for this data set, the 25th percentile, all right, how would we do it? Well, how many observations are in its data set? There's 8, correct? So we take 8 times our desired percentile value, which is 25, divide that by 100, and we get 2. Since C is a whole number, all right, the 25th percentile will literally be the mean of the second and the 2 plus 1th or the third value in the data set. So the 25th percentile is going to be the average of the second and the third observation in this data set. The second observation being 7, the third observation being 11. So the 25th percentile is the average of 7 and 11, which gives us 9. 9 would be the 25th percentile for this data set. Notice 9 is not actually a data point in the data set. So a percentile value may or may not actually be in the data set as a data value. All right, so this is the criteria we're going to use, ladies and gentlemen, for computing percentiles and finding percentile values. We're going to use this formula coupled with this formula here. So this is the way we're going to crank them out. And please also do this for Alex. If Alex complains, I will investigate and get to the bottom of the situation and then go from there. Okay, but we're going to assume that Alex abides by this criteria, these formulas here. All right, quartiles. What is a quartile? Well, a percentile is a data value that percentiles divide our data set up in 100 equal intervals. Quartiles partition our data set up into 4 equal size intervals, hence the word quarter. Quarter means 4. All right. And ladies and gentlemen, the first quartile, denoted as Q sub 1, is going to be equal to also the 25th percentile of our data set. The second quartile, Q sub 2, is also going to be known as the 50th percentile of our data set, or it also has another name. It's called the median that we looked at last week. The median, or the middle value of your data set, is the second quartile. The third quartile is going to be the 75th percentile also of your data set. Okay. Now, how do we find quartile values? Well, one way is to make sure your data, first of all, is sorted. And we could use the percentile formula. In other words, to find the first quartile means to find the 25th percentile. To find the second quartile means that we want to find the 50th percentile. Or to find the third quartile, we want to find the 75th percentile. That's one way to find your first, second, and third quartiles. But there is another way. The other way is, once we have our data in sorted order from lowest to highest, left to right, the second quartile is going to be the median of the data values, literally the middle value of your data set. We've seen how to compute that from last week. Your first quartile, which is the 25th percentile, is going to be the median of the data values less than your second quartile. The third quartile, the 75th percentile, will be found by finding the median of all the data values that are above your second quartile. Another useful statistic is called the interquartile range, IQR. It is nothing more than the difference between the third and the first quartiles of your data set. Because it's the difference between the 75th and the 25th percentile values, we say the IQR roughly is a measure of the middle 50% of your data. Okay, the IQR value is the middle 50% of your data. All right, here's an example to breathe life into all this. Suppose we have resting heart rates for 9 people and they're measured. Notice the data initially comes at us unsorted. First thing we need to do is order our data. We did from smallest to largest, left to right. And then, ladies and gentlemen, notice there's 9 values in our data set. So to find the median, since we have an odd number of data values in our data set, the median would be the middle value, below of which would be 4 observations, and above of which would be 4 observations. So the median, or the second quartile, or the 25th percentile, would be 76. 76 is the middle of this data set. 4 observations below, 4 above. There are 4 values less than 76, namely 64, 69, 71, and 74. So to find the first quartile or the 25th percentile, all we got to do is find the median of the lower 4 data values. And since there's an even number of data values below the median, 4 observations, the first quartile, or the 25th percentile, is going to be the average of the middle 2 data values of the lower 4. So the first quartile is going to be the average of 69 and 71, which gives us 70. The third quartile, or the 75th percentile, is going to be the median of the upper four data values, those that are above the median 76, which is going to be the average of the middle two values, 83 and 89. So the third quartile is 86. The interquartile range then would be 86 minus 70, which would give us 16. Okay, so the middle 50% of the data is 16 units wide. All right, any questions how we're computing quartile values here? All right, what's a decile value? Well, deci, ladies and gentlemen, means 10. And so decile values take our data set and partition our data set up into 10 equal size intervals. All right. So we have our first decile value, which is D sub 1, below of which lies 10% of your observations. D sub 2 is your second decile value, which corresponds really to the 20th percentile. So notice your first decile, D sub 1, is really your 10th percentile. D sub 2, your second decile, is really your 20th percentile, et cetera, et cetera. So D sub 7 would be your 70th percentile value. All right. So those are deciles. All right. I remember that when we were talking about measures of central tendency, we've discovered that the mean is very sensitive to what are called outliers in your data set. Data values that are uncharacteristically larger or smaller than most the other representative data values in the data set. At that time, I promised that we would eventually show you an exact numerical way of specifying whether a data point qualifies as being an outlier. Well, that time has come, ladies and gentlemen. So again, an outlier is an extremely high or an extremely low data value when compared to the rest of the data values in a data set. And they kind of stick out like a sore thumb. They kind of stick out, you know, and kind of like slap you in the face and say, I don't really belong to the rest of this data. Okay. For instance, if I had a data set that had data values in it of like 2, 4, 5, 6, 7, and 8, and suppose there was another data value in that data set that was like 50,000. Well, I think it's safe to say that 50,000 probably would be an outlier in that data set. Do you agree? Or if I had a data set that had data values in it of like 5, 10, 15, and 20, and suppose I had another observation that was in that data set that was like negative 100. Well, obviously, it looks like negative 100 just does not fit with the other data values. It would probably be an outlier. All right. So, ladies and gentlemen, we say that statistics that are highly sensitive to outliers and whose values are greatly affected by outliers in a data set, we call those statistics non-resistant. We call a statistic a resistant statistic if it is invariant or unaffected, if you will, by outliers. Examples of non-resistant statistics would be such measures of center, such as the mean, the variation, the variance or standard deviation, and position are all affected, adversely by outliers. Resistant statistics would be like the median or the interquartile range. They're not affected by outliers. All right. Now, as a result, if your data set is skewed to the right or to the left, positively or negatively skewed, we really should be using the median, okay, as a measure of central tendency as opposed to the mean. And the middle 50% of the data will be indicated by the IQR value, the interquartile range value, again, being the difference between the third and the first quartile. Okay. Determining the normality of your data set or the skewness of your data set also is required when you start doing inferential statistics on data, because it will dictate whether you are to use what's called a parametric statistical test versus a non-parametric statistical test. All right, how do outliers ever, become a part of a data set? Well, there can be many reasons. It could be simply attributed to data collection errors. Whoever's collecting the data, maybe they, did an erroneous input, or maybe they just jotted down a data value wrong. All right. There are times, however, ladies and gentlemen, when outliers actually do occur just because of random chance. It does happen, but most of the time outliers are attributed to measurement errors or recording errors, or data collection errors. Okay. All right. Now, how do we detect outliers? Well, how do we determine if a data value is an outlier or not? All right. Well, I mean, you could kind of eyeball it, kind of determine it from that way, but we like to be more precise. And here's an exact numerical test to subject the data value to see if it indeed is an outlier. First, we want to sort our data. Then we want to find our first and third quartile and compute the interquartile range of the data set by taking the difference between the third and the first quartile. Ladies and gentlemen, then we're going to multiply the IQR value by 1.5. And now here's how it works. Any data value in your data set that is less than your first quartile minus 1.5 times your interquartile range, or any data value that's greater than your third quartile value plus 1.5 times your IQR value, we would classify those data values as being outliers in the data set. Okay. Sometimes we call this 1.5 times the IQR value a fence value. We call it a fence value. Fence. So, to put this more succinctly, an outlier is any data value that's less than your first quartile minus 1 fence value, or greater than your third quartile plus 1 fence value. Let's try to breathe life into this. Here's a data set to illustrate how we would determine this. This data set has been sorted already for us, left to right, smallest to largest. And ladies and gentlemen, we find that the first quartile would be 70 and the third quartile would be 86. We find those values by the aforementioned formulas. The interquartile value would be 86 minus 70, or 16. Now, what would be the lower boundary and the upper boundary, okay, or the cutoff values, if you will, for outlier values? Well, the lower boundary is going to be the first quartile minus 1.5 times your IQR. So it's going to be 70 minus 1.5 times 16, or 46. Any data value that has a value less than 46 is an outlier. So any data value that's less than 46 is an outlier. This is the upper boundary of our outliers. Any value that is greater than our third quartile plus 1 fence value would be classified as being an outlier. So for this particular data set, any value that is greater than 110 would be classified as an outlier in this data set. So, are there any outliers in this data set? Do we have any data observations less than 46? No. Do we have any observations greater than 110? Yes. 195 would be an outlier in this data set. Everybody see that there? 195 is an outlier. All right. How do we do, some of this on our calculator? Well, ladies and gentlemen, we can, I'll tell you what, let's go back to this data set here. Let's bring up our calculator here. Hold on a second. I gotta get out of this. All right, let's bring our calculator up. Now what I'm going to do is I'm going to type in this data set. I'm going to type it in unsorted. Stat, edit, in list 1. Here goes the data set. That's if I can type correctly. Just be careful with data entry. And I got to be extra careful with this application because there's always a little lag between when I hit a key and when I see it. And that's a major problem. So I got to go slow. It's always wise to check your data before you subject it to an analysis or any sort of computation, just to make sure you typed it in correctly. All right, so I'm going to scan through my data. It does look like it's okay. I'm going to sort my data by hitting stat, go down to sort in ascending order for list one. And now list one has been sorted. Let's go back to stat, edit, and take a look at our sorted data. And there it is. All right, ladies and gentlemen, now to compute the first quartile, 25th percentile, second quartile, 50th percentile, 75th, excuse me, third quartile, 75th percentile, we can go to, get out of this, second mode to quit, stat, go over to calculate and use the 1-bar stats function. List one, leave the frequency list alone, leave it blank, calculate, and boom. Here is the 5-number summary for our data set. The 5-number summary consists of the minimum value, the first quartile, the second quartile, the third quartile, and the maximum data value in your data set. This is called the 5-number summary of a data set. Five-number summary of a data set. That's what they mean when they say find the 5-number summary of a data set. That means to find the min value, the first quartile, second quartile, third quartile, and the maximum value. All right. Do we get the same values that they got by using their formulas? You know, we're lucky. It looks like our TI-84 obeys the same formulas that are laid out on the PowerPoint or in your textbook. We got the same value for the first quartile, the median, and the third quartile. Looks like we're in luck here. That's a good thing. If you try to find these quartile values using maybe Excel or some other statistical software program, you may not get precisely these same values. All right, I'm just warning you. All right. So now we know how to do a little bit of that on our calculator. Okay, so that is section 3.3, ladies and gentlemen. Now maybe we can go to our textbook and see if we can have a little bit of fun. Let's see if I can get out of this. Okay, let's go to our textbook. All right, open up our textbook, go to section 3.3. Measures of position. Let's go down to where the problems begin, right in here. Let's see if we can have some fun. Okay. All right. Now, problem number 8. To which percentile, quartile, and decile values does the median correspond to? Does anybody want to weigh in? The median of a data set is the what quartile value? Let's do that one first. That's the easiest one.
The second quartile.
That'll be the second quartile. What percentile would this be equal to? Second quartile is also the what percentile? That's the middle of the data set, correct? So that'd be the what? The 50th percentile? And does anybody want to take a wild guess as to what decile value it would be? What decile?
Is it the 5th?
It would be the 5th decile value. That's dead center between, dead center in between 0 and 10, correct? There you go. So the second quartile is really the 50th percentile, which is also the 5th decile. All these are equivalent data values of the data set. Make sense? That's for problem number 8 there. All right, let's see what else here. Let's go down to number 9. It says the daily caloric intake, according to the dailymail.com.uk website, people eat on average 3,770 calories per day. That's a lot of calories. 3,770 calories. I'm just comparing that to, like, if you get on a treadmill, ladies, I'm going to walk for 30 minutes, maybe at a speed of 4 miles per hour. You're not going to be burning no 3,770 calories. That's so not happening. You'll be lucky to get up to about 100, 120 calories. Do you agree? Wow, that's a lot of calories. Now it says, if the standard deviation is 325 calories, find the z-score for each raw score. Ladies and gentlemen, what would be the z-score for 3,250 calories? Remember, a z-score gives us an indication as to how many standard deviations the data value is away from the mean of a data set. Well, to compute the z-score of 3,250, I like to represent it this way symbolically. Put z and put a little subscript of 3,250. This means we're computing a z-score for this data value that has a value of 3,250. To do this, we take the data value, which is 3,250. We subtract off the mean of the data set. And the mean, they tell us, is 3,770 calories. And then we divide this by the standard deviation of the data set, which is 325. So go ahead, get on your calculator and tell me what the z-score is for the observation 3,250 calories. Oh, wait a minute, that should be 320. No, I'm sorry, it is 3,250. What's the z-score for 3,250 calories? Anybody? What do we get?
Negative 1.6.
Negative 1.6. And therefore, can anybody in plain English explain to us what this is saying? What is that negative 1.6 saying? Anybody? How do we interpret what that z-score value is saying? Negative 1.6. Well, what it's saying is that it's saying that the data observation 3,250 is 1.6 standard deviations below the mean. So if this is the mean, which is the 3,770, this value of 3,250, ladies and gentlemen, right here, is 1.6 standard deviations below the mean. So this 3,250, do you agree, is really X bar, we're assuming this is a sample, minus 1.6 times what? Lowercase s. Do you agree? Isn't that what it's saying? 3,250 is 1.6 standard deviations below the mean. So it's equivalent to X bar minus 1.6 times the standard deviation of this data set. Correct? That's what it's saying. All right. Now, I want you guys for classwork number 1, I want you to do the rest of these, B through E. I want you to convert all of these data values into z-scores. And because the screen has got cut off, I'll indicate that the mean is 3,770 calories. And the standard deviation was 325 calories. Go ahead, ladies and gentlemen. Do B through E. That'll be classwork number 1. Go ahead and take care of that. I want the z-score for every one of these data values. All right. Did anybody get the Z-score for 4,160 calories? Let me ask you this, just by looking at it, is 4,160 calories going to have a Z-score that's positive or negative? Is it above the mean or below the mean?
Positive.
It's above the mean.
Positive.
You better have a positive Z-score. Yep. And what would it be? Anybody got it?
1.2.
1.2. That is correct. All right. How about for 3490? What would be the Z-score?
Negative 0.86.
Yeah, it should be negative because 3490 is less than 3770, the mean of the data set. And we discover that, yeah, 3,490 is about almost one standard deviation below the mean. Almost, not exactly. Negative 0.86 is the Z-score for 3490. How about for 4320? What's the Z-score? Well, it's got to be positive because it's greater than the mean.
1.69.
All right, yeah, so 4,320 calories would be 1.69 standard deviations above the mean caloric intake of 3,770 calories. All right, finally, the Z-score for 3,615 would be negative 0.48. That's almost a half a standard deviation below the mean, okay? So any questions about computing Z-scores? They're pretty easy to compute, all right? All right. Now, another question here. Number 13. This is classwork number 2, ladies and gentlemen. Classwork number 2, it says, which is the better relative position? A score of 83 on a geography test that had a mean score of 72 and a standard deviation score of 6, or a score of 61 on an accounting test that had a mean score of 55 and a standard deviation score of 3.5? To answer this question, the hint is you have to what? You have to standardize both of these scores. In other words, convert them into Z-scores and then compare the Z-scores to answer the question. Number 13, classwork number 2. Go ahead and do that one. Now, ladies, on both these Z-scores for the score of 83 on the geography test and 61 for the accounting test, both those Z-scores are going to be positive or negative. What would be the case? Anybody?
Positive.
Positive. Okay, if they're both positive Z-scores, what are we looking for to determine which score is the better relative score? What are we looking for? The Z-score that's the greater Z-score or the smaller Z-score? What do you think, if they're both positive?
Is it the smaller one?
Well, the smaller Z-score indicates that the score would be closer to the mean or the average of the class. Do you agree? The larger the positive Z-score
Okay.
indicates that the score would be what? Higher above. Do you agree? The mean or the average of the class. All right. Did anybody get the Z-score for the geography exam score of 83?
1.83.
All right. Anybody get the Z-score for the accounting test score of 61?
1.71.
Exactly. And so therefore, ladies and gentlemen, notice that the geography test score is higher above the mean score, and the accounting test score is not as high above the mean test score. So therefore, the geography test score, relatively speaking, is the better score between the two exams. Does that make sense here? Okay. You see, if you don't convert these test scores into Z-scores, then it's like comparing apples and, kangaroos. It's just not going to happen because you're struggling with two different aspects of this test, namely the mean and the standard deviation, which is a lot different than the mean and standard deviation of the other test. So you have to level the playing field by turning these scores into Z-scores, because now these Z-scores indicate the relative nature of the test score to the mean and the standard deviation of all the test scores for the particular courses. Okay. All right, so we're done with that one. Okay. Next one. All right. Now, problem number 17. They give us a data set. And ladies and gentlemen, they want us to find the data value that corresponds to each of the percentile values. In other words, for this data set, they want us to find the 40th percentile. What data value in this data set would be the 40th percentile? I got a question for you. Which formula do we use? Do you remember the formula? Let's see. Hold on. Let's see here. We're trying to find the percentile of a data value in our data set. So we know we want to find the 40th percentile. Do you agree? So we're going to use this formula right here. This criteria right here. So jot that formula down if you haven't done so. C is equal to N times P divided by 100. Remember, if C is not a whole number, then we round up to the next whole number, and that would be our Pth percentile. If C is a whole number, then the Pth percentile will be the average of the Cth and the C plus 1th data value in the data set. So that's the formula we're going to have to use here, all right, to answer this question in number 17. So C is equal to N times P over 100. Let's go back to our problem in our textbook. And we want to find the 40th percentile in this data set here. First of all, what are we going to have to do with the data? Step number 1.
Sort it.
You got to sort the data first, all right? So pour it into a list in your calculator and sort it in ascending order, ladies and gentlemen, and just try to answer the question A here. What data value, what data value, according to this equation, this formula, would be the 40th percentile value of this data set? Okay, go ahead and do that. We'll call this classwork number 3. All right, go ahead and do that. All right, how are we doing out there? Put all the data in the list and your calculator, sort it in ascending order. And then, ladies and gentlemen, you're going to have to use this formula that's in our PowerPoint. So we're trying to find the 40th percentile. That goes in for P. There's 27 observations in the data set. 27 times 40 divided by 100 gives us a rank of 10.8. According to the PowerPoint slide, if C is a decimal, we round up to the next nearest whole number. So therefore, the 40th percentile has rank of 11 in this data set. So you go to your sorted data in your calculator and you count up 11 ranks, and you will discover that the 11th ranked observation in the data set is 21. This is your 40th percentile. Did anybody get that?
Yes.
21. That's your 40th percentile. See how we're doing this here? Okay. So that's a classic example that you'll run into on Alex, et cetera, et cetera. Finding a percentile of a data set. Please do use the formula on the PowerPoint. Okay, let's see what else we got here. Okay, just finding some more percentiles. Find a percentile. Okay. All right, now, ladies and gentlemen, we're going to work backwards. In this data set here, they want us to determine what percentile value 67 is. So in this data set, 67, the data point observation of 67 is what percentile values? What percentile value is that? So we're answering the opposite question now. Well, let's go back to our PowerPoint presentation here. Now we're going to have to use what? This formula to find what percentile 67 is. So we have to count how many observations are below 67, add 0.5 to that, divide by the total number of observations in the data set, multiply by 100, and therefore, ladies and gentlemen, we will then be able to determine what percentile value we will have. Okay, so that's the formula you have to use for this next question. Number of values that are below 67 plus a half divided by the total observation, number of observations in your data set times 100. All right, go ahead and do that. We'll call this classwork number 5 here. Number 5, classwork. Wait, was this 4, 5, 6? I don't know. If I lose track, don't worry about it. You're just going to hand it in with all the other ones anyways by midnight. All right, that's our next classwork. Do that one. Find out what percentile value this is. So we're trying to find out what percentile 67 is. Okay, go ahead and do that. News is we hopefully have the data still in our calculator, and so we don't have to reinvent the wheel here. All right, I have my data sorted on my calculator here. We want to count how many observations are less than 67. So let's go down to 67 here, right here, and now start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. There's 23 observations, ladies and gentlemen, less than 67. All right, now we use our formula. There's 23 observations less than 67. So 23 plus 0.5 divided by the total number of observations in the data set times 100 gives us 23.5 divided by 27 times 100 is 87.037, which we round off to the nearest whole number would be the 87th percentile. So it looks like 67 would be the 87th percentile. Did anybody else get that?
Yep.
All right, so we good on that? Is this making sense, how we're doing these two different types of problems? Here we're being asked to find what percentile data value is. Up here, we were being asked to find what data value was a particular pth percentile value. Two different questions being asked there. All right, that's good. Okay. Now, all right, now, number 18. Let's see if we can go down here and get into trouble. No, they don't let us do it for 18 there. Let's see. Percentiles. 15 percentile. Okay. Well, number 18 here. They want us, ladies and gentlemen, to approximate the 30th percentile of this grouped data set here. Okay, this is group data. All right, and how do we do it? Well, we have a frequency distribution table here. So this is how we're going to do it here. This is not a classwork problem. Okay, I'm going to demonstrate this one. What we're going to do is we're going to add on another column here, and it's going to be called the cumulative frequency column. So I'm going to add on another column here. This is the cumulative frequency column. Okay. And then we're going to have another column at the end, which is going to be called the cumulative percent column. Cumulative percent. Cumulative percent. Cumulative percent. Cumulative percent. Okay. All right, here we go. Now, just like when we built an ogive graph, we had to do a cumulative frequency distribution first. So, by the time we cut through the first class, we have what? 9, right? By the time we get up to 248 or 248.5, if we have boundaries, right? By the time we get up to 397.5 or 397, we've cut through the second class. So 9 plus 16 is 25. By the time we get up through 546 or 546.5, if we had boundaries, we've got to add another 19. So what's 25 plus 19? That's going to be 44. 44 of the observations have been accounted for. By the time we get up to 695 or 695 and a half, we got to add 28 more. So we have accounted for 72 of our observations. By the time we get up to 844 or 844.5, we add on another 17. We've accounted for 89 of our observations. By the time we get up to 993 or 993.5, we got to tack on another 7 observations. It's 96 observations. And by the time we get up to 1142 or 1142.5, we basically have encompassed our entire data set. So we now have accounted for 100% of our 100 of our data values. These are not percents. These are just the number of data values that have been accounted for. To turn these into cumulative percents, we're going to divide each of these cumulative frequencies by by 100. So 9 divided by 100, turning it into a percent would be what? 9 per 100 is what, 9%? All right, what's 25 divided by 100? That'd be 25%. 44%. Now these are percents, ladies and gentlemen. It just so happens that there were 100 observations in this data set. Okay, how nice is that? 72%, 89%. You're not always going to have that in data sets, 100 observations. This is a utopic situation as far as percents are concerned. Okay, all right. So I have a question. Approximately what would be our 30th percentile? Where's 30% approximately here in this last column? 30% is like right in here. Do you agree? So, ladies and gentlemen, what would be our, our 30th percentile approximately here? Well, let's see. 30th percentile. Okay, let me see something. Did they do midpoints in here? 30 is about what? Halfway? No, it isn't. 30 is closer to 25 than it is 44, correct? All right. So 30th percentile is going to be, it's going to be, somewhere in between like 397, somewhere in between like 397 and I'd say like 398 about 8-ish. Okay. So it's going to be somewhere in here. Okay, the 30th percentile. You can see that finding percentiles of group data is a little bit more of a guesstimation. All right, because we don't get nice cumulative percentages, which are exactly equal to the percentile that we're being asked to find. All right. Raw data is a lot easier to compute percentiles for because we do actually have a formula. All right. Group data, like I said, is a little bit more laborious as far as finding percentile values is concerned because we're dealing with classes here. Okay. But that's kind of like gives you somewhat of a snapshot as to what's going on here. And if you wanted to graph this thing here, you would go up to about, let's say 248. You could even use class boundaries here, or probably class boundaries would be the best way to go, like 248.5 here. Okay, that would be like the 9th percentile by the time you get up here. So you would lay off a scale here on the vertical axis. These are percentile values on the vertical axis here. And so like 248.5 would be about what, 9%. So you put a point right here about. And 397.5. Okay. By the time you get up to 397.5, you're up to the, what would be the 25th percentile. 25th percentile would be like right about in here. And then up to 546.5, you'd be up to the 44th percentile. 546.5. You would be up to 44%, 44th percentile. So there's 40 and there's 50. So 44 is going to be like right in here, something like this. And what you're going to do is you would then connect these dots. And by the time, you keep going up through these classes here, you're going to get all the way up eventually to what? Your 100th percentile. Okay. By the time you get all the way up here. So that's kind of like how you would make a percentile graph. There is actually a graph that is illustrated in section 3.3. You're welcome to look at that as to how they build this. It's on page 155. That illustrates how they build a percentile graph, ladies and gentlemen, for a group data set on page 155 in your textbook. All right. All right. So that, I believe, is good enough for this section here. Oh, well, let's see. Yeah, it's good enough for this section here. Let's get out of this now and move to the last section. The good news, the last section is a lot shorter than the first section. Okay. So section 3.4, entitled Exploratory Data Analysis here. All right, and when we get done with this very short presentation, we're going to use the techniques of exploratory data analysis, including box plots and the 5-number summary of a data set to discover various aspects of the data. Okay, so we're going to learn how to build another graph for a data set. This graph is going to give us a good idea as to the variability that exists and also the symmetry that exists or does not exist in a data set. All right, exploratory data analysis is nothing more than a method for examining data to see what can be discovered about its center and maybe its spread without making conjectures about the nature of the data. And again, it's also a nice way, ladies and gentlemen, of organizing our data in a very interpretable way. We've already seen the stem and leaf plot that we built earlier, the dot plot that helps. All those things help organize our data and give us a more accurate snapshot as to what the data is trying to tell us. Okay. The 5-number summary is going to be required in order to build what's called a box plot for a data set. Of course, the 5-number summary consists of the minimum value in a data set, the first, second, and third quartile values, and the maximum value in the data set. Right? All right, so what is a box plot? How do we build one? Well, to draw a box plot, ladies and gentlemen, first of all, we have to have a horizontal axis at the bottom of our box plot, and it has to have a relevant scale on it as far as the data is concerned that is being studied. So we need to know the range of our data. That helps us to lay out accurately the scale on the horizontal axis below the box plot. And then to build a box plot, we're going to have to compute the 5-number summary of a data set. We're going to need the minimum value, the first quartile, the second quartile, the third quartile value, and the maximum value in the data set. And if you're doing a whisker plot, you would also want to indicate if there's any outliers in your data set on your box plot diagram. Okay. All right, so how do we make a box plot here? Well, the way it works is the left edge of our box, okay, projects down to the horizontal axis to the appropriate first quartile value. Okay, so you can see this top box plot, the left edge projects vertically down to 49, so that would be our first quartile. 58, the middle partition of this top box plot, projects down to 58 on our horizontal scale down here, about 58. That's your second quartile, that's your 50th percentile. 67.5 projects down to the horizontal axis at 67.5. That's your third quartile or your 75th percentile. Of course, the minimum in a data set needs to project down to the minimum value on the horizontal scale, and the maximum value would be 72 for this data set. It projects down to about there. Okay, so that's basically how you make a box plot. You need the 5-number summary, and then you can build your box plot. But of course, you obviously have to have an accurate scale below the box plot. All right, and your first, second, and third quartile min and max values have to line up with the appropriate number on the scale. Okay, so I'm not sure what this data pertains to. Pertains to 2 different roller coasters. It looks like a wooden versus a steel coaster. But what do these numbers represent here? I don't have a clue. Well, anyways, I want to show you, ladies and gentlemen, what box plots can tell us. We're comparing 2 different roller coasters, wooden versus steel, whatever the numbers pertain to. I'm not sure what they are. But let me ask you this question here. Which box plot is longer, the top one or the bottom one?
The bottom.
The bottom one. And so therefore, ladies and gentlemen, we would say that the variation of the steel roller coasters, whatever the numbers pertain to, is greater than the variation of the wooden roller coaster data set?
It's speed in miles per hour.
Oh, speed in miles per hour. Okay. So the median speed in miles per hour of a wooden roller coaster, I don't know how many wooden roller coasters they, included in their investigation. We know is 58 miles per hour. For a steel roller coaster, the average speed is about 85 miles. The median speed is 85 miles per hour. Okay. So first of all, what data set exhibited more variability as far as their speeds are concerned, the wooden or the steel roller coaster data set? Well, which box plot is longer? That would be the steel roller coasters. So the speeds of the steel roller coasters are more spread out, okay, about the mean or the median of this data set. There's more variability with the steel roller coaster data set as opposed to the wooden roller coaster data set. That's what we can gain real quickly just by looking at the relative lengths of the box plots. Number two, which median speed is greater, steel or the wooden roller coaster median? Well, that's obvious. It's the steel roller coaster median that's further to the right on the horizontal axis than the median of the wooden roller coaster. Okay. And that intuitively makes sense, as steel roller coasters normally go a little faster than wooden roller coasters, probably for safety concerns, obviously. All right, now another thing, ladies and gentlemen, we can determine is this, the symmetry that the data possesses. For which box plot, the wooden roller coasters or the steel coasters, is the median halfway in between the first and the third quartile? Which one?
Looks like the wooden one.
Yep. Therefore, because the median speed of the wooden roller coasters looks like it's dead center between the first and the third quartile, we would say that the data set for the wooden roller coasters is normally distributed, symmetric, and bell-shaped. Do you agree? Normally distributed, symmetric, and bell-shaped. So if you were to build a histogram for these speeds, you would expect the tallest occurring bar to be in the middle, and then they would fall off with equal frequency to the left and right of that center highest bar. Do you agree? So this wooden roller coaster data set is symmetric and bell-shaped. Notice the steel roller coaster speeds exhibit some skewness to them. In fact, since there's more box between the first quartile and the second quartile, as opposed to between the second and the third quartile, we would say that this data set is skewed to the left. So if you were to build a frequency, histogram, you would discover that this frequency histogram would look like something like this. Okay, it's skewed to the left, ladies and gentlemen, or negatively skewed. So box plots can tell you a lot of information very quickly. They aid our ability to compare two or more data sets very quickly. They also aid our ability in determining the variation that exists within a data set. And they also enable us to get a quick snapshot as to the symmetry or the normality that a data set exhibits or does not exhibit. So box plots are very useful. All right. Okay, any questions how we built this box plot? You got to find a 5-number summary to build a box plot. That is required. Now, obviously, you have to have your data sorted to do any of that. Okay. All right, here's an example. Suppose that we have these observations in a data set. Notice, luckily, they are sorted from smallest to largest, left to right. To build a box plot, we have to find the 5-number summary. The minimum value would be 5.7. The maximum value is 49.7. The median, since there's 10 observations in the data set, the median would be the average of the middle two. So the median would be literally the average of 18.7 and 20.9. That's the second quartile or the 50th percentile or the median, which is 19.8. The first quartile or the 25th percentile would be the median of the lower 4 observations. which is going to be the middle value of these two values. So the first quartile will be in the average of 9.1, 11.8. Would give us what? Oh, there's five. Wait a minute. 1, 2, 3, 4. No, there's 5 values. Let's see. 1, 2, 3, 4. Okay, look at. Got to be careful here. The median is dead center between 18.7 and 20.9. So there's 5 observations less than the median. 5. Careful there. There's 5 observations less than the median, which again, the median is right in the middle here. So the middle value of these lower 5 would be 11.8. 2 to the left and 2 above. That would be your first quartile. And the third quartile, or the 75th percentile, would be the median of the upper 5 values, the 5 values that are above the median. And that's going to be 29.8. That's your third quartile. All right, now, and the maximum, we got all that, we got everything now. We can build our box plot. So we, underneath our box plot, put in a horizontal number line, and we have an appropriate scale so that we can see our box plot. And our box plot ranges from about 5 up to about what, maybe 50 at least. So the author decided to lay out a scale by 5 this way, and then you can build your box plot. 5.7 drops down to this value here. 11.8 drops down to here. 19.8 is about like right here. 29.8 is about like right here. And your maximum value is 49.7 right here. Okay. Got a question for you, ladies and gentlemen. Are there any outliers in this data set? Any outliers? Do we remember how to find outliers? Always comes down to memory. Any data value that's greater than your first quartile plus 1.5 times your interquartile range. Your interquartile range is the difference between the third and the first quartile. Will be an outlier. Or any data value that's less than. Wrong. That's not right. This should be less than. Less than. Or any observation that's greater than your third quartile plus a fence value. Your third quartile plus 1.5 times your IQR, your interquartile range for this data set, would be considered to be an outlier. Okay. So what I want you to do right now, ladies and gentlemen, is get on your calculator and dial up for me. What's the lower end point? What's the upper end point? Or the cutoff values for outliers? Go ahead and compute these values here. They give you everything. You got everything here to do that. So go ahead and do that. So what's the cutoff value for a low or small outlier? And what's the cutoff value for a large outlier? Anybody getting 38.8 from this guy?
Yes.
Okay. Now let's do the upper cutoff value for an outlier. Got to figure out this one.
I got 56.8.
Yeah, that's 56.8. All right. Now that we got these two values, between these two values, you would not have an outlier. Any value that's more extreme than any of these values would be an outlier. Do we got any observation in this data set that's less than 38.8? Wait a minute here. Is that right? Well, let's see. We did compute these correctly, right? 11.1 plus 1.5. Wait a minute. Well, I am not having a good day, ladies and gentlemen. This should be a minus here. I do apologize. We got to recompute this lower one here. This should be Q1 minus 1.5 times the interquartile range. My bad. This one is correct, though. The 56.8 is correct. Let's recompute the lower boundary. It's got to be minus. All right. All right. Let's see if we can get it now. What is this lower value here? Anybody get it? I'm getting like negative 15.2. Anybody concur? Can anybody concur with that?
Yes.
All right. So is there any data value less than negative 15.2? No. Is there any data value greater than 56.8? No. So are there any outliers in this data set? The answer is no. No outliers. Make sense? No outliers. Suppose, just for illustrative purposes, what if we had a data value that measured 55, not 55, that's like, say, 60 in this data set? How would we represent it on our box plot? Well, ladies and gentlemen, there's 60 on a horizontal scale. We would put a little asterisk. We would put a little asterisk right there. And we would call this a whisker plot, okay? This is like a little whisker here. This would represent that you have an outlier. This would be an outlier. Suppose you had a very small data point in this data set. Maybe way down here. This would be an outlier. You denote it by putting little asterisks, okay? That's how you would do that. All right. Does that make sense how we're building box plots and, manually? And you could use your calculator using the 5-number summary from your calculator also to speed this up. Can a calculator build a box plot directly? The answer is yes, ladies and gentlemen. And I'm going to show you right now how to do that. Okay, let me clear out all the garbage here. Okay, let's bring up our calculator here. I'm going to show you how we can build a box plot on your calculator directly. Okay. Okay, let's type in the data in list 1 here. How to build a box plot. Okay, you got your data in, and again, just make sure there's no obvious erroneous entry. All right, how do we build a box plot? Well, pretty simple. Let's get out of this second mode to quit. Let's go into our stat plot mode. To get into our stat plot mode, we have to hit our second key followed by the Y equals key. Second Y equals button gets us into stat plot. Second Y equals. Notice I have 3 stat plots at my disposal. Are all of your stat plots turned off? If not, if you have any stat plot turned on, I want you to move your cursor down to plots off, hit enter again, that'll turn them all off. Let's go back to stat plots, second Y equals. Now all your stat plots are turned off. Let's dive into plot number 1 by hitting the enter button with the cursor sitting on plot 1. Toggle it on, hit enter. It's now been turned on. Hitting your right and down arrow keys, let's navigate till we get to the box plot icon. Ladies and gentlemen, this is a box plot icon, but I want this one that would also include the possibilities of also plotting outliers. This is a box and whisker plot icon. Always choose this one. It's more robust than that one to the right. Hit enter. Notice my data has been put into list 1. The frequency, leave it as 1. And all the other stuff is just cosmetic as to what kind of mark you want to delineate the point location and what color you want. Hit enter. All right. And we can get out of this mode now. It's on the second mode to quit. We configured plot 1 to build a box plot. Clear your screen. Go to zoom now. Hit your zoom button at the top of your keyboard, zoom, and go down and select the zoom stat function. What this function does is it basically looks at your data set real quickly behind the scenes and basically constructs an appropriate scale so that we will be able to see the box plot. Okay, so it basically computes the range of your data very quickly behind the scenes. Just hit enter and select the zoom stat function and boom, you should see your box plot. Do we see a box plot? Anybody?
Yes.
Now look, you can navigate along this box plot by hitting your trace button at the top of your keyboard, the trace button, and you can navigate. There's the minimum value in your data set. There's the first quartile, second quartile. There's the third quartile and the maximum value in your data set. That's your 5-number summary. Do you agree? Now you can build up to 3 different box plots for 3 different data sets. If you had another data set, you would put the data in list 2. And then you would put the data in list 3 for a third data set. And then you can build up to 3 box plots because notice you have 3 stat plots at your disposal. Okay. And that's a nice way to compare data very quickly by building box plots that are aligned vertically. All right. Okay, ladies and gentlemen, let's go see. We're running out of time here. Let's go back to our textbook quickly. See if we can do maybe a problem here. Section 3.4. Let's go down to the problem set. Problem number 10. Can anybody tell me what the 5-number summary is for this data set? What would be the minimum data point in this data set? Approximately, what would be the minimum?
525.
Looks like about 525. What would be the first quartile or the 25th percentile? About what? 550? All right, the left edge of the box. What would be the second quartile or the 50th percentile? Or the median?
575.
575. And what would be the third quartile or the 75th percentile? Looks like about what, 600? And what would be the maximum value in the data set? 625. All righty. See that? Does it appear this data set is symmetric or is it skewed? And if it's skewed, is it right or left skewed? What do you think?
Looks symmetric.
Very symmetric. I mean, that second quartile is like dead center between the first and the third quartile. That looks like an extremely symmetric, bell-shaped, normally distributed data set. Okay. All right. So you can just tell just by looking at these box plots what's going on here. Hey, between 7 and 8, which data set exhibits? Wait a minute. We can't say that. We can't say that, ladies and gentlemen, because look at the scales. The scales are radically different, aren't they? Sorry about that. Can't do that. Can't compare them. You can only compare them if you only have one scale underneath multiple stacked box plots, then you can compare them. All right, forget that. Here's what I want you to do here. Okay. All right, ladies and gentlemen, I want you to build a box plot for data set number 12. This is the last one. We'll call this the last classwork, okay? Use your calculator to speed this up. Put the data into a list and build the box plot. Go ahead and do that. Last classwork. All right, so we basically type in our data, right? Put it maybe in a list. I'll put it in list 1. And then building the box plot is pretty simple. Second mode to quit. Go to stat plot mode. Dive into plot 1. Make sure it's turned on. Select the appropriate icon, which is the box plot icon. Data's in list 1. Everything looks good. Then zoom and zoom stat. Boom, you got your box plot. Okay. All right, ladies and gentlemen, did we get that or not?
Yep.
Does it appear, is there an outlier in this data set? Looks like there's an outlier, doesn't it? You see this little box over here? Normally it's an asterisk in most stats books, but let's find out what it is. Just hit the trace button here. Hit the right arrow key. The outlier would be a data value that is 8,186. That's considered to be an outlier. Apparently that's greater than your third quartile plus 1.5 times your interquartile range value. Do you agree? Does it appear this data set is symmetric or highly skewed? What do you think? Pretty symmetric. That middle partition, the second quartile, is roughly, halfway between the first and third quartile. That's a fairly symmetric data set. Pretty close to being bell-shaped or normally distributed. Yeah. All right, so we are done. We have covered measures of position. We looked at percentiles, deciles, quartiles. We looked at 2 different types of problems involving those. The first type of problem was given a data value, we wanted to determine what percentile it was, or given a data set, we wanted to determine what data value in it was like a pth percentile. Then we looked at the 5-number summary and how can we use to build a useful plot called a box plot. And we looked at how to analyze a box plot as far as determining if our data set is symmetric or skewed and what type of variability it exhibits. Okay. If your box plot is very short, ladies and gentlemen, in other words, if you have a box plot that looks like this, that means that there is a very small standard deviation or variance in this data set. all your data values are clumped up very close around the mean and the median. If your box plot is like this, okay, then we would say that the variance or standard deviation is very large. Okay, data values are highly dispersed around your mean or median. All right, and we also determine whether our box plot or data is symmetric or skewed. If your box plot looks like this, it would be what? Skewed to the left. If your box plot looks like this, it would be skewed to the right. Okay. All right, so that's it. You guys have a great weekend. I'll try to open up everything that I mentioned at the beginning of class on Alex, and hopefully you can get that done by the due date, ladies and gentlemen. I'm not supposed to tell you this, but I do allow a 2-day grace period, believe it or not, from the date I want your assignment to be turned in. There is kind of like a 2-day grace period in which after that point you would then be penalized 10%. But see what I've done now? I've turned us into more of a procrastinator. So I should not have even have said that. Try to get it in by the due date that I have on the schedule, ladies and gentlemen. All right. But if an emergency arises, a big time emergency, you have a 2-day grace period before the penalty is assessed. All right, have a good day. I'll be on the line for a couple minutes. If you have any questions or concerns, please let me know. Okay.
Thank you. Have a good day.